So I had actually started the typing in a different way. That also I didn't bring. In any case, so basically I am talking about the unit 4. Unit 4 of your syllabus has a second part, and that is about Maxwell's equations. That is charged electromagnetic charged particle in an external electric and magnetic field. So I just start with how do we talk about covariance of Maxwell's equations. BAK has explained it to you, but it is a kind of review for you. Now, in electrodynamics, you have a concept called as charge density and current density, and your Maxwell's equations are given by these 4 equations. That is, what you are looking at is basically a charge distribution. Any charge distribution is characterized by rho of RT. That is charge density, which changes at different points of space and time. Rho divided by epsilon naught. Epsilon naught is a constant. It is permittivity or whatever it is called. Divergence of E is rho by epsilon naught. This is a kind of analog of Coulomb's law, and divergence of B is 0. The curl of E is minus dou B by dou T. Curl of B is 1 over C square dou E by dou T plus mu naught J. Mu naught epsilon naught is related to inverse square of light, velocity of light. Now, these equations involve electric and magnetic fields as well as charge density and current density. What is given and what is to be found out here is, given the charge density, you know what is the electric field. Charge density and electric, that is current density. Your job is to solve these differential equations to obtain electric and magnetic fields, given the charge density and the electric J vector current density. Now, I have this charge density rho, current density J. Now, if I put them together, it can be called as 4 vector, a 4 vector in special relativity, and I write the contravariant components of J mu as C into rho to match the units. J has a unit and current density rho into C has same units as current density. That is, this is a charge density multiplied by C carries same thing as current density. Remember, we used to have 4 vector, space-time 4 vector X mu has 4th component C into T to match the length dimension, and the third 1 to 0th, hello, 0th component is CT, and 1, 2, 3 components are vector R. Similarly, here I constitute a vector like this, and notice that electrodynamical equations of continuity can be expressed in a covariant fashion. So now, what is continuity equation? In electrodynamics, you come across this kind of a equation. I am just talking about some familiar notions and writing it in the covariant form, because special relativity has that covariance. Is what we started our day with in special relativity is to say Newton's equations are covariant under Galilean relativity, but Maxwell's equations are covariant under some other transformations. They are called as Lorentz transformations. That's what was the first observation by Einstein. So now we have, so once Einstein talks about covariance, you should be able to see it. That is, how is that electrodynamics is covariant under Lorentz transformations? In order to do that, covariance requires a transformation, and I have to express everything in terms of a 4 vector or a tensor quantity and whatever is required, scalar, tensor, vector, in that language. So I consider a Minkowski space and I constitute a 4 vector J mu, of which C0 is the 0th component and J is the 1, 2, 3 component. It's a vector. We had earlier, we used to treat rho separately and J separately, like how we treated space separately and time separately. But now I put them together and look at what is our continuity equation. Our continuity equation has a dou rho by dou T plus divergence of J equal to 0. That is the governing, any any charge density that is known to you, any current density that is known to you associated with a physical charge distribution and current distribution obeys this continuity equation. That's a consequence of, that's a law. Continuity equation is obeyed by every charge distribution and current distribution associated with a charge current distribution. Now, I write this equation in a covariant form. Covariant means I should express it as some kind of dou mu, j mu. Then I can write dou mu prime, j mu prime in some other frame of reference. I have explained you what is covariance. I write this equation as dou mu, j mu equal to 0. Why? Because what is dou mu? If I write a dou mu, it's a derivative. I know what is a three-dimensional gradient operator. I introduce dou by dou x naught, that is x naught is ct. Then I get a 4 vector here. This transforms like a 4 vector can be shown, but you can check that dou mu. I'm writing it right now, but verifying it, how does it transform under Lorentz transformation requires some writing, which I can't do today. So dou mu is 1 over c dou by dou t and del operator. And j mu, as I said, I have constructed it like that. Now you write what is dou 0, j 0. Dou 0, j 0 is 1 over c dou by dou t multiplied by c rho. It will be dou rho by dou t. Okay. Then plus del divergence of j. Divergence of j is here. Divergence of j. So this equation can be written as a covariant under Lorentz transformations. In one frame of reference, it is dou mu, j mu. In another frame of reference, it is dou mu prime, j mu prime, which is 0. So this law, left-hand side is whatever form is covariant. It is a covariant form. So now, the four-dimensional version of the Laplacian, I write a Laplacian. What is a Laplacian? Laplacian is 1 over c squared, del squared by dou t squared minus del squared. Three-dimensional Laplacian is only del squared. Okay. I expand the Laplacian into four-dimensional version of Minkowski space-time and write it as a D'Alembertian. This is what is D'Alembert. Now I write this square and write it as four-dimensional Laplacian or D'Alembertian 1 over c squared dou squared by dou t squared minus del squared. This is a differential operator and it is kind of generalization of Laplacian in the space-time. So now I write this. This can have a covariant form. You can write this as g mu nu dou mu or dou mu because you have what is dou mu. I have written it here. So you should remember this. Why I wrote it? I can prove that dou mu transforms like a covariant component of any 4 vector. That can be shown. I am not able to show it to you. Some other time I will try to show. Otherwise, it is not, unless I send you questions, then it is difficult. Any questions there? I heard some. Okay. So now I write this D'Alembertian operator as dou mu. This is also a Lorentz invariant generalized Laplacian differential operator. It has the same form in any frame of reference. Now, Maxwell's equations, you know it. So now what we try to do is to learn about Maxwell's equations. We know that any scalar and vector potentials phi and a can be introduced to express electric and magnetic fields. What are physical? Physical is electric and magnetic fields. We do experience electric and magnetic fields in our labs. But how does this come? Cos is charge density and current density associated with some charge and current. So I do experience, that is impact. If effect is E and B. So I need to determine what is the effect E as a reason of the electric field and current density and charge density. That is Maxwell's equation. So I want to find out electric field, which is 3 components. It as a function of XYZ, B as a function of XYZ. But what I will do now is to write these E and B in terms of vector potential A and scalar potential phi in this particular way. This is our what is called as SI units basically. Otherwise, I write a 1 over C here and all that. I have written all this in terms of SI units. Electric field is minus dou A by dou T minus gradient of phi. Magnetic field is curl of A. In other words, instead of 6 components of electric and magnetic field has 3 components, magnetic field has 3 components. And Maxwell's equations written here, they are to be solved to find 6 different components, 6 components of electric and magnetic fields. So, but I can do it with 3 components of vector potential and 1 scalar potential. 4 quantities can be determined if I write it in this way, and I can then find out electric field. If I know A and phi, I can determine what is E and B. That is the whole philosophy. So I have written it. It is introduced for mathematical convenience. 6 components of electric and magnetic field can be defined in terms of 4 components of scalar potential and vector, that is vector potential and scalar potential. Now, I try to say that what is your electrodynamics, what you have learned. Let us have a review. If I take a transformation, I consider what is called as a gauge transformation. These are called gauge transformations. I can replace vector A by vector A plus gradient of some unknown function. Any function is fine. Write an unknown function. Function of what? Function of R and T, space and time. I write this. I am talking about electrodynamics and some familiar notions when you learned electrodynamics. If I replace A by A plus gradient of phi and scalar potential phi by phi minus same chi, dou chi by dou T, then physical electric and magnetic fields remain invariant. That is the exercise. I would have written it and shown it to you. This is here, electric field. You replace A by A plus gradient of chi. Write it there. So A plus gradient of chi. Gradient of chi, if you have, you can write it as gradient of dou chi by dou T. That's all you can do. Minus gradient of phi. What is it? You substitute it. Then the resultant, what you, after you write A prime and phi prime given here. This, call this as A prime, call this as phi prime. The resultant quantity is same electric field. No change in electric field. If you replace A by A prime, phi by phi prime. This is called as a symmetry operation. That is, even if I change the internal electric field, vector potential and a scalar potential, your physical electric fields and magnetic fields do not change. It is like saying, we will play a blindfold. I will tie some, you have a blindfold. Once I open it, you will see what is the cube. I give you a cube and I show it to you, but I turn the cube. You are blindfolded. Once you repeat it, remove it, you will not be able to see any difference. Like that, if I write A and phi, the way it is, you wrote it. But somebody else is given a prime and phi prime. What is the result? Electric field. That is what is physically seen. There is no difference. Electric field is the same. Magnetic field is the same. If I know that, that quantity, that is called as a gauge symmetry, and transformations are called gauge transformations. This is an observation. If I introduce A and phi, there is an advantage and there is a symmetry associated with it. You can choose A and phi. Somebody else can choose A plus gradient of phi, phi minus dou chi by dou T. No problem with physical fields. What do you choose for A and phi? That is left as a blank question. Now, what do you choose is a question. Now we say there is some kind of a condition called Lorentz gauge condition. The function chi, I have to fix the function chi. I will want to, it is totally arbitrary here. I fix it. What I do is fix it by imposing Lorentz gauge condition. What I do is, I will say, if I have this equation, 1 over c square dou phi by dou T plus gradient of A is equal to 0. I take this such that the function, gauge function has a property. I need not do it arbitrarily. The gauge function has to satisfy the Laplacian, 4-dimensional Laplacian equation or D'Alembertian equation. Del squared chi minus 1 over c square dou squared chi by dou T squared is equal to 0. Let me repeat. How do you fix chi here? It is quite arbitrary. Fine, you can choose arbitrary, but I want to have little boundaries for me, because otherwise I feel, I don't know. So I want to fix it in the sense I want to choose some subset of phi which are good enough for me. I don't need more than that. Then I will impose a condition that phi and A satisfy this particular condition. These are details which are worked out, but I can't do it now. I would have done it if I had a hand where I can show it to you. Right now, I don't have a board, hand, and all that. So I will only say what is written here. This I impose so that if I impose this condition, if you change A to A plus gradient of phi going to this condition imposes that gradient squared chi, the del squared chi minus 1 over c squared, dou squared chi by dou t squared is 0. This is a differential equation. You know the solution, suppose. Then I will restrict to solutions of this kind only when I do a transformation like that. Gives me some hold. I am restricting to a subset of chi which satisfy this equation so that electric field and that is vector potential and phi, they have this kind of a condition. This condition which is used to fix chi to a known solution is called as Lorentz gauge condition. That is, with that condition, I can choose any chi which is a solution of this differential equation. Now, Maxwell's equations for electric and magnetic fields can be reduced. Maxwell's equations are 4 equations for the vector potential, electric field and magnetic field. We reduce it to only 2 uncoupled second order differential equations. That is, it can be done. I am not doing it. So these are equations for vector potential and scalar potential. What do you do? What is given here? I have a current density J. I have a charge density rho. Solve this equation. This is inhomogeneous because if it is equal to 0, I would have said vector potential A satisfies a homogeneous second order differential equation. But now I have a right hand side which is non-zero. So given this function, I have this kind of equation. So I need to solve it. This kind of equation is called inhomogeneous second order differential equation. I want to solve it given J and rho. Instead of Maxwell's equations, you choose to solve these equations. Then you do have A as a function of R and T, phi as a function of R and T. Then determine your electric field and magnetic field in this way. This way. You know A, you know phi by solving those conditions, and then write EB. E can be determined by what you solved for A and phi. 3 components of A and 1 phi are determined by the inhomogeneous differential equation. Done. Once I do this, I go back and find what is required for me. Physical electric fields and magnetic fields are determined. So now, I now come to special relativity. With this background, I again introduce electromagnetic 4 potential vector. I call A mu, contravariant component of a 4 vector A mu as the scalar potential divided by C and a vector potential A. How did I decide it? It is something which makes me gradually, when I work on it, I do know that this forms a 4 vector. That is the identification by Einstein in his 1905 paper. That is, he talks about how magnetism can be written as in a covariant manner. You define electromagnetic 4 vector potential A mu as phi by C and A. And all our laws show that this is indeed a 4 vector. So it transforms like a 4 vector under Lorentz transformation. That can be shown. I am not able to show it now, but this is what is there. And what is Lorentz gauge condition? I showed you what is a Lorentz gauge condition. That is this one. This is nothing but this equation can be written compactly as a covariant equation. Dou mu A mu is equal to 0. It's such a short form. You have to write what is dou 0 A0 plus dou 1 A1 plus dou 2 A2 plus dou 3 A3. Do you know what is gradient dou mu? That is for covariant component of del operator. You should check it. I have defined all those things here. You have to do this exercise, and this equation is nothing but the Lorentz gauge condition. In other words, Lorentz gauge condition has a Lorentz covariant form. That's what is one thing. Then I write the uncoupled 2 equations in terms of one 4 vector equation. That is dou mu up dou mu down. This is a scalar differential operator. Dou mu, and A nu. That is equal to mu naught J nu. Now you substitute what is dou mu. It is nothing but del squared. That is, I have, oh sorry, it is what is called as 1 over C squared, dou squared by dou T squared minus del squared operator. That is Laplacian operator acting on A0, A1, A2, A3. Take one at a time. Mu is a free index. This is a summed index up and down. So you have to write it explicitly to see that it is nothing but this. Again, an exercise. You have to just substitute what is. I have given you all the components of del mu. I have given you all components of A mu. You have to substitute it and get experience to write the equations, Maxwell's equations written in terms of vector potential A and scalar potential phi. That takes the form which is a covariant form. That is this form. Now, I write another one under gauge transformations. I can write these two equations as gauge transformations in a 4-vector sense. A contravariant mu goes to A contravariant mu minus dou mu chi. You can check it. What is A mu? You have it. You can write this into 2 sets of equations or write it in a covariant form. That's what is important. Everything should be written in a covariant form. That is the exercise that we are doing now. Now, what is covariant form of gauge function chi in the Lorentz gauge? We had a Lorentz gauge condition. We are trying to learn everything in covariant way. This is the Lorentz gauge condition. But that means I have dou mu. Where is it? Okay. I have dou mu chi is equal to 0. That's what is the condition. Now, we should know that components of the contravariant derivative dou mu is given by dou mu is G mu nu dou mu. I have already defined this covariant component given to you. So then you can write it as 1 over C dou by dou T minus del. I am emphasizing that these are important. Once you know what is a covariant component, you can write a contravariant component. I wrote a covariant component. How? I know it. I cannot show it to you today. So that's what is the kind of idea where you develop one by one. And we define what is called as a electromagnetic field tensor. I said there is all vector quantity, scalar quantity, tensor quantity are defined based on what transformation that you are interested in. Our transformations we are interested in is Lorentz transformations here in this particular case. We are talking only about Lorentz transformations. If I say a tensor, it is a tensor under Lorentz transformations. I want to write electrodynamics in terms of 4 vectors and in terms of tensors, second rank tensors, and it goes on like that. I define an electromagnetic field tensor, its definition, with covariant indices. That is, I write a covariant index and then define contravariant. I define it. So F mu nu is defined as dou mu, that is covariant component dou mu, A nu minus dou nu A mu. What is A mu? Covariant component. I have defined what is, where is it? A mu. A mu is here, defined, already defined. A mu down is known to you then. So if one is given, you can determine other. So A mu is pi by C, same component for time, but space component is changing sign. So write this quantity, okay? Dou mu, this is given by this. With this, it is your exercise now. You have 2 indices. You have to write 2 indices. F00, you have to work out F00. Shall I give you time to do it? Write what is F00. Don't look at what is given here. Will you tell me what is F00? Substitute it. F00 means dou 0, A 0 minus dou 0, A 0. Are you with me?
Yes, ma'am.
Tell me what is the result. F00. Don't substitute, simply write dou 0, A 0 minus dou 0, A 0, correct? Don't substitute all this.
0, ma'am.
0. So similarly, I want you to write what is F11. 1, 1. Write this and tell me. Simply write this. Don't look at these components.
0.
Okay. Similarly, you can do one quantity, F1, 2. Please do F1, 2. Dou 1, A2. Dou 1 means it is dou by dou x. Dou by dou x. A2 means AY with a minus sign. Minus dou by dou x of AY. That is first term. Minus. What is dou nu? Dou nu is 1 over C. Sorry, 1 over C forgotten. 1 over C dou by, no, not in this. Okay, please do it yourself because without hand.
Is it BZ?
No, tell me what is this. So then it is a curl of A.
Yes, ma'am. F12 is BZ. I got
component of curl of A. So I have written it here with a minus sign. Please know that it's a minus sign. So you have missed it. Whoever answered this question, there is a minus sign. For me, I get a minus sign. Do you get a minus sign? Please check it. What did you get here? Then you should write it properly. Okay. Curl of A, what component? Is it a plus curl of A or minus curl of A?
Ma'am, I got plus, ma'am.
You got plus?
Yes, ma'am.
Okay, let us work it out then. Please tell me because I have to see what you are writing from my mind. So first component is
dou 1 A2 is dou AY by dou X.
Minus dou AY. You see here, A mu is given here. Okay, minus sign, first term. There is a minus A.
Yes, ma'am. Then it's minus.
That you have to be extraordinarily careful when you substitute. Okay, A covariant component is defined like this. A upper component is defined by this plus sign. If you do, that's why I am very careful when saying covariant indices of the field tensor are given by is this way. Okay, everything is given here. You have to work it out. You know that the F mu nu has electric field and magnetic field in this way, and by construction I have defined it by construction. This construction tells me that F mu nu field tensor is an anti-symmetric second rank tensor. Second rank because it has two indices, and it can be shown that under Lorentz transformation how we transform. It is easy to show. So easy means if you know it very well. So I call this as a second rank anti-symmetric tensor which involves components of electric field and magnetic field. Now, in non-relativistic dynamics, you would have treated electric field as a vector, magnetic field as a vector. But these two are put together in the form of an electromagnetic field tensor, not a vector. So we say electric field and magnetic field are components of a second rank tensor. Like how X and T get mixed as a 4 vector, electric field and magnetic field are one unit. It is called as an electromagnetic field tensor. Electric field and magnetic field, there is no difference. They get mixed up when you have Lorentz transformation. That is the mathematical property. Indeed, you know it. If I have a charge, I hold a charge and somebody is moving with under a Lorentz transformation. If I say it's an electric field only because it's a static charge, the person who is moving with velocity v in a different frame, he says, no, there is a magnetic field also. because he is moving with a velocity v. The fixed charge looks like a current to the observer. So we do see such a intuition by saying that electric field and magnetic field get mixed up under Lorentz transformations, like how x and ct are momentum and energy, they get mixed up. That is, they are units of one whole unit of a quantity. The name of that quantity is an electromagnetic field tensor, and it shows that by mathematical properties, the electric and magnetic fields are not vectors of space. They are tensors of rank 2 under Lorentz transformation. It's an electromagnetic field tensor. Components of that are given by electric field and magnetic field. Having defined that, how and all, it takes a long time because you have studied it already in your electrodynamic class. I am repeating it, but this is required for doing charged particle in an external electric and magnetic field. So now, components of electromagnetic field tensor with one covariant and one contravariant can be defined. You have got F mu nu. Do an exercise. Given this F mu nu, you are now doing Lorentz transformations. You have a metric tensor. The metric tensor is known to you. G metric is diagonal. And what are its indices? It is down or up, whatever it is G, like this. So I want to write a F first index mu, little space nu. How can I do that? I will say it is F mu, one index down, alpha nu. With the help of a G alpha nu, F, I am not changing mu, I am changing only nu. I write nu with alpha and the index alpha. Alpha, alpha are contracted. You have a F mu nu written in the left hand side. This needs some practice to write it. But carrying out a calculation is much easier. It is to multiply your F as a written as a matrix here. This is F mu nu matrix. That matrix, F mu nu, and G with mu first and nu later. That is the matrix multiplication. So multiply F into G. You have G, you have a F here. You get what is a mixed tensor, F mu nu. So you will find that explicit 4x4 matrix form for the field tensor by doing this exercise, F into G. This is special relativity notations. So once I do this, I get what was electric field remains as a minus electric field. Electric field changes sign and magnetic field changes sign again. Minus BZ becomes a plus BZ, etc., etc. in this kind of a format. Now, similarly, you can write both contra components, F mu nu here. So how do you write it? You have to write a G mu alpha, G nu beta, F alpha beta. This can be, that is how am I writing it? I know I want to have lowered indices. So to lower a index mu, I need to have a mu alpha, G mu alpha. And then I write a F alpha, first index. Second index, I have to do it. I write a G nu beta and write a beta here. Now, write mu alpha. These are all numbers. You can shift it wherever. G mu alpha, F alpha beta middle, and G nu beta. You write it in that way. Then you know that alpha gets contracted, beta gets contracted. Write it in that particular way. Then it can be written as a matrix G, F, G, mu nu. Because free indices are mu and nu. F mu nu upper index is equal to GFG upper index. This is how I can write it. This is a simplification. I am using what is upper rising and lowering of indices. Once I do that, I get explicit 4x4 matrix form for the field tensor. Now again, you notice what has changed here. B has not changed. Bx, by, bz with a minus sign, it is remaining. But electric field, what was electric field in F mu nu here? It is plus here, but it is minus here. That is slightly changed. It's like saying, if I have a 4 vector, which is x mu, what is the time component? Ct. Space component is vector r. But if I lower the index, time component is Ct, space component is minus r by calculation, mathematical calculation. Like that, I learn what is field tensor with both contravariant components, both covariant components, and mixed components. Exercise for you. Having done that, I do notice some properties now. List the properties. F mu nu is an antisymmetric tensor. That is F mu nu. If you change mu and nu, that is given by minus F mu. How do you check it? Take the explicit form and check it. F mu nu by definition, you can see that. Change mu and nu, you write a F nu mu, then you get do nu A mu minus do mu A nu. So you have to write whichever, how do you write it is a question. Minus of do mu A mu. It is not possible to explain it. You have to work it out. You know that F mu nu is equal to minus F mu mu by this definition itself. I am listing the properties now and I will show you this. So F mu nu is a second rank tensor under Lorentz transformation. So by that I mean F mu nu prime is equal to L mu alpha, L nu beta, F alpha beta. I have to write for covariant indices what is the transformation. Mu, if it is there, I have to write a L mu alpha. That is one part. And nu, I have to write a nu beta. So some index is fine here. You have to write the same index here. This can be written in a matrix form. Matrix form is always easy than the index form. So I always play between indices and matrices. But to write matrices, you should know which are the indices that you are choosing to write a matrix. So I am writing F prime is L, F, L transpose. You follow whatever I have said, you get experience with writing it. I have struggled to write these notes by not making any mistake. There could be mistakes still. So F prime is L, F, L transpose. So then I will say, remember, what are the transformation properties of tensors in Minkowski space? This was the first unit had all this. That is, what are four vectors? What are tensors? Tensor and this thing. Covariant component of a four vector transforms under Lorentz transformations as T prime mu is dou x alpha by dou x prime mu T alpha. Or if I write a T prime mu, it is L mu nu T nu. What is L mu nu? You have to write a x as a function of x prime. Write x alpha, that is express x in terms of x prime vector. Then you do get this. Again, I can't, my hands are bound. So contravariant component can be written like this. This you can work out. A dou x prime mu, x prime is L into x is what we had said. So you do get a L first index mu, second index alpha. This is the contravariant tensor property which I had explained to you. Other one is a covariant, L mu nu here. Now, covariant components of a second rank tensor can be defined like this, where the dou x alpha by dou x prime mu, this one is L mu nu. I have written a L mu alpha because alpha is there. Similarly, x beta, x prime beta is L nu beta, T alpha beta. That's what I have done to define a second rank tensor. That is mathematically what is it. So now I also defined one more quantity that is called as a dual tensor. So a dual tensor, F curly F mu nu, I define it in terms of what are called as Levi-Civita symbols of four indices. You know Levi-Civita symbol epsilon ijk, but down. But now I have to define contravariant Levi-Civita, covariant Levi-Civita, mixed Levi-Civita, all that comes. But I am only defining here, stick to this alone. So what is epsilon mu nu rho lambda? That is given by +1 for even permutations. Write this as 0, 1, 2, 3. And cyclic ordering, it will give you +1, 0, 1, 2, 3. And then you can write 3, 0, 1, 2 or 2, 3, 0, 1 like that, cyclic. Then it is +1. Interchange any two of the indices, you get -1. Same way you go ahead. And if you have same number of indices, mu and nu are same, you get a 0. That's the definition of this. So now I define a dual field tensor F mu nu in this particular. Having defined it, it is your job to find out what is the structure of a dual tensor. I have worked it out. If I worked it out, I get this particular. What is dual tensor? Given the F rho mu lambda, I have given it already. So work it out. Now you do get, wherever you had an electric field, you get a magnetic field. It is changed. Electric field and magnetic field interchange their places. B becomes a time kind of a component. E becomes a space component, kind of a structure. 1, 2, 2, 3 kind of things. F01, 02 are space-time mixing kind of indices for a tensor. So I have to work it out. These are all little exercises which you have to do. I define a dual tensor and I observe again that dual tensor is again antisymmetric. You know, this is 0. Wherever there is a minus bx, there is a plus bx here, antisymmetric. So EX is at minus EZ. So this can be seen clearly, explicitly, that it is a antisymmetric tensor. And this is a second rank tensor under Lorentz transformations, but its transformation properties are given by L transpose inverse F L inverse. This again, I cannot explain. I'm giving it to you. But that is, I have to work out what is the transformation property of this whole quantity here, whatever I have written here. And I have to work it out. That if I do that, then I get a result. Result is it transforms in this particular way. That is the statement for right now. It is a statement. Having done that, I can write Maxwell equations have a covariant form. I have to do all this exercise to show that Maxwell's equations have a covariant form. Now exercise is you have a F mu nu up here. It's written in a matrix form, right? It is there. What is F mu nu? Where is it? This is the F mu nu. You have to pick this. I send you these notes. Pick this and then work out what is, how many equations are there. At least you can count how many equations are there in this one. Can you tell me? How many equations are contained in this? Suppose I ask you, I give you dr by dt is equal to v. Write it in a component form. Can you tell me how many equations are there? Dr by dt is equal to v, vector v. Dr vector by dt is equal to vector v. How many components, how many equations should you write? Hello?
3, ma.
Now, same way you have to be counting this. Now,
4.
4. Here 2, here 4 again. So write these equations first, okay? Write these equations, that's the exercise. Given F mu nu and given the components dou mu, write down left hand side, identify that it is mu naught into J1, J2, J3 and J0. What is J0? It's a row, correct? So you have 4 equations here, 4 equations here. Total 8 equations. But if we go to Maxwell's equations, how many equations are there? Let us see that. Divergence of E is equal to rho by epsilon naught. How many equations? It's counting equations. What is this quantity? Divergence.
Only one, ma'am.
What is divergence of E? Is it
Scalar.
a scalar vector? It's a scalar. This is a scalar equation. So how many counts?
1.
1. You write 1 equation here. And this one?
1.
1, 2, 1 plus 1, 2. Now this one?
3.
3. This one?
3.
3 plus 3, 6, 6 plus 1, 7, 7 plus 1, 8. So you have to write 8 different equations, which is done in a covariant way. That's what is important here. You have written a Maxwell's equation in a covariant way so that you are ensured that if you go to a different frame, you have Maxwell's equations. It is not somebody's Usha's equations or some Meda's equations, Chetan's equations, Nitin's equations, whoever are there. It is Maxwell's equation written in a covariant way. I have to follow that rule. One Maxwell will give you equations. You use it in any frames of reference. That's what is these equations. I will stop it with saying only one. This should be verified. And then we define, this is very important, covariance of Maxwell's equations. And I have some things called as invariance. Now, I explain it to you in one particular way. Given a vector, 4 vector x mu, can you construct a scalar from it? Question. Given a 4 vector x mu, can you construct a scalar? And if you construct a scalar, can you tell me what is it? That's how we started our life with. Yes. Yes. Scalar means Lorentz invariant. Okay. A vector means transforms under Lorentz transformation with one Lorentz factor x mu nu, L mu nu. Second rank tensor means two L's appear, kind of thing. So now scalar, it doesn't change. It's a Lorentz invariant quantity. Given x mu, I give you for vector x mu. You have only x mu. Can you write a invariant? Or let me put it in another way. I give you a 3 vector A, write a scalar of associated with the vector A. That is why we call it a scalar product. A dot A is a scalar product. Given A, you do a operation and tell me that is a scalar. Okay. Same way, given a x mu, you construct a x mu, x mu, x mu, x mu, up and down. That is a scalar product. What is the value? It is x squared, c squared t squared minus x squared minus y squared minus z squared. That is an invariant. That's how we started our life with. Maxwell's equation, that is any Lorentz transformations, preserve the length x squared, c squared, t squared, minus x squared, minus y squared, minus z squared. So with a vector, you can construct some invariants or Lorentz scalars. Like that, we will ask you, if you are given a tensor, second rank tensor f mu nu, and its dual tensor f mu nu, how many independent Lorentz invariant quantities that you can find? We have only 2 can be proved. I don't prove it. F mu nu, if you take a f mu nu and f mu nu, contract it one from another. This is a Lorentz scalar because I have contracted a tensor indices. Tensors is a mathematical branch where you learn these things, that contracting will kill whatever is a factor. So mu and nu, both indices are killed here because you have inner product of f mu with mu, nu with nu. If you construct such a quantity, I call it a invariant one. And you notice that this invariant explicitly worked out because you know f mu nu, you know f mu nu, write one by one. Take mu is 0, 0, f 0, 0, f 1, 1. It's summed over. All 6, however many numbers are there, you have to write it. Then you will get bx squared plus by squared plus bz squared is called b squared. It's a scalar product of b with b dot b, that is b squared, minus e squared by c squared. This is what is the quantity which is an invariant. If you write tensor notations, you will be able to see what remains as a Lorentz invariant. Suppose you have a frame of reference where you have applied only a magnetic field, let us say, only a magnetic field. Then what is this invariant I1? I will say, look, I1 is positive. B squared is there. Only B squared is there. Then I will say, you go to any other frame of reference, I1 may be B prime squared minus E prime squared by C squared, but this number is same. Like how you found B squared, that number is going to be same in another frame of reference. So I will say B squared minus E squared by C squared is going to be positive. If you had only B squared in one frame of reference, in any other frame, you will also have an electric field. So there it is B squared minus E squared by C squared. That should be positive. In one field, if it's only magnetic field, in another field, because of the invariance, B squared is positive, one frame. Another frame, B squared minus E squared by C squared should be positive, associated with the same observation. Charge is there, there is a B squared. Current is there, there is a B squared. Another frame, you will see charge and current both. So you have B squared minus E squared by C squared. But the value should be, number I1 should be same. So number I1 is positive in one frame of reference. In another frame, it should be positive. We call, remember we had called something as space-like vector, time-like vector, etc. Here with the invariants, I can say that this is like a magnetic field. That is, B squared minus E squared by C squared is magnetic. If B squared is, if this quantity is positive, always positive means even if there is an electric field, B squared minus E squared by C squared is positive means I can go to a frame of reference where there is only magnetic field, no electric field. That's what we can say because we know Lorentz transformations, it's mathematical property. Similarly, I take a dual tensor, I can construct like this. That is going to be 1 over C B dot E. So the scalar product B dot E remains the same. If electric and magnetic fields are perpendicular in one frame, in every frame of reference under Lorentz transformations, it is going to be same. That is, the perpendicular nature will not go. If they are perpendicular, what is B dot E? If B and E are orthogonal, what is B dot E? What is A dot B when A and B are orthogonal?
0.
So orthogonal, perpendicular, crossed electric and magnetic field means I2 is 0. I2 is 0 when electric and magnetic fields are orthogonal. I can talk about a Lorentz invariant concept. Electric and magnetic fields are orthogonal. Look, similarly in special relativity, you have learned that simultaneity is not a good concept. Simultaneity is not Lorentz invariant. So it is very important. Our notions of space-time, it said, if I say it is simultaneous, some other frame of reference will say it is simultaneous. But under Lorentz transformation, simultaneity is not an invariant concept. You have learned it. Similarly, here, I will say there is an invariant concept. You remember that. If B dot E is given to be, let us say, some value, non-zero value, positive value, then it could be same in any other frames of reference. Angle between B and E remains the same, and strength of magnetic field and electric field, difference between them, that remains as a constant. So if B is equal to E by C, I1 is 0. We say that electric and magnetic fields are equal in strength up to a constant C. Magnetic field is always weaker than electric field by 1 over C, always. Magnetic field is weaker. In a electromagnetic equation, say for example, light, we are considering light. Light is characterized by B and E with same magnitude. Remember that? Electromagnetic wave has same electric field, magnitude of same electric field and magnetic field up to a factor C. In SI units, there is a C coming in. So this I1 is equal to 0 in such a case. And if B is perpendicular to B, then E is 0 in all Lorentz frames of references. Now notice that I1 is 0, I2 is 0, characterizes electromagnetic, freely propagating electromagnetic wave. Okay, because we do know that light is given by equations which are electric field of light is equal to magnetic field of light with up to a factor C, and electric field and magnetic field are perpendicular. You draw such pictures for pictorial things for electric and magnetic fields. Now you are learning the mathematics behind it. And the mathematics is there are two Lorentz invariant quantities. I1 is 0, I2 is 0. Now, I say that if B dot E is 0 and this is 0, one can choose an appropriate Lorentz frame so that only electric field exists. If I1 is equal to B squared minus E squared by C squared, if it is negative, I can make B 0 and this other thing is minus E prime squared by C squared. Only electric field exists, so that it is shown to be negative. So I can go to choose a Lorentz frame of reference where complicated both electric and magnetic fields will not be there. I calculate I1 and I2 and check, is I1 positive or negative? If I1 is negative, I can choose a Lorentz frame so that only electric field exists. And if I1 is equal to positive, then I can choose a Lorentz frame of reference where only magnetic field exists. This is of great calculational importance because you apply in your lab both electric and magnetic fields. Do you know to solve the equations? Very difficult. I will say go to a Lorentz frame of reference mathematically to choose only electric field or magnetic field. Check what is I1. If I1 is positive, you can go to a frame of reference where only magnetic field is there, no electric field is there. Now solve your Lorentz force equation. That is the way we should work out. So that is what is done in the next lecture, where I have charged particle in crossed electric and magnetic fields. So this invariant concept and other things should be learned. I didn't bring all the lecture notes and I scribe and all that, but I hope you have understood what I said. I will formulate this in terms of problems and you have to work it out. Okay, this one because I don't know, you have to work it out. Whatever problems, I share it with you later, little later, because I have to wait till I go home. Here I have some other one. So I will stop it here. Any questions?